Welcome to This Explainer. Today, we're diving into the absolute ultimate everyday mystery of our natural world. Why is the sky above us blue? We literally look at it every single day, right? But the actual mechanics behind that brilliant blue canopy, well, they're absolutely fascinating.
It's kind of the classic question, isn't it? Curious minds of all ages have asked it. But to actually unravel it, we have to start by completely rethinking how we see sunlight. It feels like such a simple question for sure, but the answer? It requires us to look at invisible forces all around us, bridging this incredible gap between the vastness of space and, well, the biology of our very own eyes.
So, let's jump right into section 1, the anatomy of sunlight. What exactly is in a sunbeam? Okay, so sunlight might look perfectly white to us as it beams down on a beautiful clear day, right? But it's actually this crazy mixture of all the colors of the rainbow. Think of it like energy passing through the ocean. This light travels in waves. And here's the kicker. These waves are not all the same size, not even close. On one end, we have these short, super choppy waves, and those make up the blue and violet visible light. And then all the way on the complete opposite end of the spectrum, you've got these long, lazy, rolling waves that make up the red and orange light.
So what actually happens when this big mix of white sunlight enters Earth's atmosphere? Well, it immediately slams right into tiny air molecules. We're talking primarily nitrogen and oxygen here. And because that blue light is traveling in those short, choppy waves we just talked about, it gets intercepted. It basically crashes into these molecules and scatters in literally every direction. That scattered blue light then bounces all around and eventually reaches our eyes from every single part of the sky above, which makes the whole thing look vividly blue.
All right, moving on to section 2, the scattering phenomenon, or how light collides. Now, this brilliantly illustrates the whole concept in the real world. Just picture a flashlight beam shining directly through a glass of perfectly clear water, and compare that to one shining through water mixed with just a few little drops of milk. In the clear water, boom, light passes straight through, no problem. But those drops of milk, they completely change the game. They cause the flashlight beam to scatter, making the water look super murky and cloudy, while the tiny gas particles in our air act exactly like that milk, scattering the sun's rays all across our atmosphere. This exact mechanism actually has a name in physics. It's known as Rayleigh scattering. By definition, it's the elastic scattering of electromagnetic radiation by particles that are way, way smaller than the wavelength of the light itself. And it's actually named after this brilliantly curious 19th century British physicist, Lord Rayleigh. He's the guy who mathematically mapped the whole thing out back in 1871, right after scientists like John Tyndall first started noticing how bright light scattered off these nanoscopic particulates. But the math behind this magic, that is where things get really fascinating. Lord Rayleigh discovered that scattering intensity is inversely proportional to the fourth power of the light's wavelength. Okay, sounds complicated, but here is the crucial takeaway. Shorter wavelengths, like our toppy blue waves, they don't just scatter a little bit more. They scatter exponentially more strongly than those longer, lazier red wavelengths. And this incredible mathematical reality right here is exactly why blue completely dominates the daytime sky overhead. Which brings us to section 3, the violet light paradox, or, as I like to call it, the missing purple sky. Think about it for a second. If violet light has an even shorter wavelength than blue light, and according to Lord Rayleigh's math, it gets scattered way, way more easily, wait, why isn't our daytime sky just a vibrant, glowing purple?
It's a great question, right? Well, the answer is this really beautiful mix of biology and astronomy. First off, the black body spectrum of our sun means it just naturally pumps out less violet light compared to blue light. Second, our upper atmosphere actually steps in and absorbs some of that violet light before it ever even reaches the lower atmosphere. And third, well, human eyes are simply much less sensitive to violet. Actually, our visual system basically processes the whole wavelength combination overhead as if it were just a mix of blue and white light.
All right, let's look at section 4, the science of sunsets, the colors of the evening. The really cool part is that we can apply these exact same rules of Rayleigh scattering to a completely different time of day. When the sun dips super low on the horizon, its light isn't just beaming straight down at us anymore. It actually has to travel a significantly longer physical distance through the Earth's thick atmosphere just to reach your eyes. So just think of it as a matter of distance. At midday, the distance the light travels through the air is relatively short. Because of that, the blue light is scattered across the sky, and we see that classic blue overhead canopy. But at sunset, that distance is long, and over that much longer journey, almost all of the blue light scatters away completely before it ever even reaches you. So what's left? only those longer, lazier waves of red, orange, and yellow. They are the only ones strong enough to punch through that thick layer of atmosphere and paint those spectacular sunsets we all love to watch. Finally, let's head into Section 5, Skies on Other Worlds, Beyond Earth. Let's start with our closest celestial neighbor, the Moon. Now, as we know, Earth has this really dense atmosphere packed with nitrogen and oxygen to intercept light. But the Moon? Zero atmosphere. None. And without an atmosphere full of tiny gas molecules to intercept and scatter that incoming sunlight, there is absolutely no Rayleigh scattering at all. Because of this, the sky on the Moon is completely, permanently black, even when the sun is shining directly on you. Crazy, right? Meanwhile, let's take a quick look at Mars. The red planet has this very thin, super dusty atmosphere that's composed mostly of carbon dioxide. So instead of just tiny gas molecules, this atmosphere is totally filled with fine, iron-rich dust particles kicked up from the surface. Because of these really specific particles and just how thin the air is, it scatters light entirely differently than Earth does. The result is this hazy, reddish, almost golden glow instead of our crisp blue. It just goes to show you that a sky's color is literally the direct signature of a planet's atmospheric chemistry. So, bringing it all back home, the crucial point here is that our everyday blue sky is actually a masterful illusion of physics, astronomy, and human biology all working together perfectly. The next time you gaze up at a clear blue sky or sit back to watch the colors shift during a sunset, I want you to remember the invisible wave physics at play and ask yourself, what other mysteries of light and nature are waiting to be uncovered, just hiding out there in plain sight?